In this problem, we're going to be working through problem 6.1, which deals with the velocity triangles in an axial compressor. The problem statement says that we're dealing with a single stage of a compressor rotating at 12,400 RPM and compressing 120 pounds mass per second of air. The inlet temperature and pressure are 140 psia and 900 degrees Rankine, respectively. The average radius of the blades is 8 inches and the inlet blade height is 1.15 inches. The absolute inlet angle to the rotor is the same as the stator exit angle, which is 18 degrees, and the rotor flow turning angle is 17 degrees. The compressor stage has been designed so that the blade height varies and the axial velocity remains constant through the stage. The efficiency of the stage is 88%, and we are asked to find the required power to drive the stage, the total pressure ratio for the stage, and the percent reaction for the stage. A couple key points in this problem statement are that we're just dealing with a compressor that could be somewhere in the middle, or a stage is somewhere in the middle of the compressor. All we really need to know is the inlet flow angle set by the upstream stator row, and then the flow turning angle of our rotor. Also, we're told that we know the average radius of the blades and the height of the blade passage. We don't know the inner and outer radius necessarily, but we're going to evaluate what's happening at a radius of 8 inches, assuming that there's a passage, basically a strip 1.15 inches tall, going annularly around the circumference. The other assumption that's put in here is that the blade height varies so that we can keep a constant axial velocity through the stage. This is a common design practice, but it's not necessarily a requirement. So basically we're saying here that even though we're increasing the pressure of our air and therefore increasing its density, so we would need less flow area to pass the same mass flow, we are going to constrict that flow area to keep the axial velocity a constant value. We can pull out our key variables here and also look up the appropriate values for gamma and Cp based on a temperature of 900 degrees Rankine. So we can say that gamma is going to be equal to 1.381 and our specific heat will be 0.2483 BTUs per pound mass degrees Rankine. And we're going to assume constant properties through this stage.